Hello, welcome back to the WVU Geography 300 Geographical Data Analysis video series. We are in the midst of trying to infer from the sample mean to the population mean. Now, this relationship of what we know from our sample to what we don't know, but what we really kind of want to know, goes through this idea called the central limit theorem, which is a way of trying to basically measure or quantify how much error we have, not in our data set, but in this value of the sample mean. It also relates, and I need to put it here, it relates to the sample size. And there is something you will see called the standard error of the mean. And I am working off of the book that I have kind of recommended for the class. I'm using it, although, as I said, it's not a required book, to make sure that everything is correct. As an aside, that should be kind of telling you, if you're the kind of person who doesn't memorize formulas really well, don't feel bad, neither am I. That's why reference materials, I'll use them. I don't judge if you use them either. So this standard error of the mean notated again with kind of borrowing off of the standard deviation of the population with that lowercase sigma, but with the mean, sample mean subscript. Now, in the highly unlikely situation, if we knew the standard deviation of the population, if we don't know the mean, we probably don't know the standard deviation of the population, but we'll just go with it for now. Is, if we knew it, it would be the population standard deviation divided by the square root of the sample size. In a theoretical world, that's what we would have. But, of course, we don't always have a nice theoretical world. So then what do we do if we don't know this? And it's important to note, before moving on, the general principles involved. This is how much uncertainty basically we have in this measurement of the mean. Two things can affect that. The standard deviation of the population and the sample size. Now notice, if the standard deviation of the population goes up, so does this value. And that should make intuitive sense. To borrow with that age idea, if all of the farmers have about the same age, if that standard deviation of all the farmers is only a few years, our sample estimate is not going to be 10 years off. It's going to be small and proportional with that standard deviation. So as this goes up, so does the standard error. If this goes down, a smaller standard deviation for the population, so does the standard error. On the other hand, the larger the sample size, then, and it goes down by the square root, the larger the sample size, the smaller this error is going to be. So we can kind of say, if I have a larger sample size, as I said, everything else being equal, then we are going to have a more accurate, more precise understanding or sample for getting our mean. Now we get to relate this to distributions, because we're then trying to get our best possible understanding of this population mean. Because of all the uncertainty in the sample, we, in a way, can best represent our understanding of this population mean through a distribution rather than a single value. The entire math behind it is complex, but we can know that this population mean is going to follow a normal distribution. We can assume it's a normal distribution. That normal distribution of our best understanding of the population mean is centered on, has its own mean, as it were, at our sample mean. So we're basically saying my best guess of the population mean is the sample mean. But there's uncertainty in that, there's deviation in that. And that standard error is the standard deviation of that normal distribution. This then gets to what you have seen, perhaps, as something called a confidence interval. And this z gets back to the z-score of what we saw before in the starting to work with inferential statistics. So instead of saying my average age is 50 years, through this I might say the standard error of that would be 5 years. But I'm not just going to go and say 50 plus or minus 5. There is, you can find them online, they're in the back of this book. I'll work with the example here. If you have a z of, if you want to know, there's a 90% chance of the range of this interval. Z is going to be 1.65 for a 95% or 90% confidence interval. So, if my sample mean is 50. Sample standard deviation is 5. I talked to 100 people. Because I don't know the population standard deviation, I will make one change here. I will take this sample standard deviation, square it, and take the square root of that whole thing. That is, even though it's very similar, that's how it is set up in the book. So then putting all of this together. So I said sample standard deviation, 5, so 25 over 100 square root of a fourth, that is going to be a half. So I come here and I say now, based upon my sample, I know there's a 90% chance that the population mean is going to be within 50 plus or minus 1.65 over 2. So I have now measured, quantified, and calculated the uncertainty based upon the characteristics of the sample. When I say, here's what I think the population mean is, my best guess is 50, there's a 90% chance is between these two numbers, 49.175 and 50.825. If I am willing to accept more uncertainty, then I would have a smaller range, I'd say an 80% confidence interval. And there are ways to look up the appropriate value of z for basically any value. Likewise, 95%, that would have a wider range instead of 90%. So I have, based upon the central limit theorem, a 90% confidence interval within that range. We can then use this to start to gauge how well our understanding of the population is through this sample. There are many other ways that this concept of a confidence interval will arise further down the line, even if the calculation of it would be far more complex than this, and basically we'll be letting the software handle those computations. I'm illustrating this here with the relationship of the sample mean and the population mean, mainly so that you can understand, here's the ideas behind this confidence interval when you see it for something that is more complex than this. We will then, for the last of these sampling videos, take this idea of the confidence interval and how it is constructed, and with a little bit of algebra, look at how we can use this to try to understand and decide how big should my sample be to have a good understanding of the population from my sample. So this is certainly the most mathematically intense video we've had thus far. As always, if you have questions, please bring this up during the class Zoom session. Reach out by email if you have any questions. And thank you for watching. I will see you at the next video.